and power conversation. Thank you so much for watching this. I really appreciate it. I do hope that you watch all the way to the end. That would be great. And we will be ready to jump in for a lab tomorrow. All right. So the first part of what we want to talk about here is the conversation that we had a few days ago about the idea of a closed system. Now, I don't know if you remember this or not, but we talked about in a closed system, that means that energy and momentum, by the way, they're both conserved, okay? So we mentioned this, we talked about this, we've kind of established this idea that energy and, oh, by the way, momentum too are conserved. They're conserved all the time as long as, and this is the key, as long as you are in a closed system. So we need to talk about what that means. We've mentioned it a couple of times, but just to make sure that it's solidly in your brain, the idea of a closed system is a system where there are no outside forces acting. So that's not to say that there aren't any forces, but all of the forces that are acting are internal. So when we talked about when we were talking about conservation of momentum, we had like cart A and it was traveling along and then it bumped into cart B and it was sitting still and then there was an interaction between them. Momentum was conserved, and the reason it was conserved is because the only force that was acting on car A was car B, and the only force acting on car B was car A. So we ignored friction, right? Because we said that it was a frictionless track, and all of the other forces that may be at play are not acting in this situation, which is why, in this case, momentum is conserved. When we talk about something falling, I don't know, like a frog or something like that, and we have it up here some height above the floor, and we talk about it having some potential energy, gravitational potential energy, as a result of being a certain distance up above the floor, and we let it go, and that potential energy then turns into kinetic energy just before it hits the floor. So now it's moving really, really fast because that gravitational potential energy is turned into kinetic energy. We can say that that energy is conserved because we're in a closed system. We have to define that closed system carefully, though. That closed system in which energy is conserved in this way is a system of the frog, we'll say consisting of the frog and the earth. If we don't include the earth, then, friends, there's a force of gravity or the force of the earth acting on the frog. So if the system was just the frog, then energy is not conserved because it starts off with no kinetic energy and ends up with kinetic energy. So in this case, again, we've talked about this a couple of times, but in this case, if we're going to talk about energy being conserved, then the system has to be both the frog and the earth. So it's very important, again, when you're talking about a closed system, and AP really likes it, which is why I'm trying to hammer it here. When they talk about a closed system is one where there are no outside forces acting. It's just important to be able to define, again, what your system is. So all of that said, my question for the day today is, what if it's not a closed system? What if it's, well, the opposite of that would be an open system, right? So a system in which, so I'm going to actually write this down. So an open system would be, well, it's exactly the opposite thing. So a closed system is one where there are no outside forces acting. An open system would be, you guessed it, when outside forces act on an object or a group of objects, we'll say. Well, friends, the trick is that if outside forces act, then things change. Then things accelerate, right? We have a couple of different situations here. I'm going to give you a couple of scenarios. So scenario one would be a situation where a force, some sort of outside force, causes an object or system. I'm just going to say object, but know that we could be either one. Object, let me spell that right. Okay. Accelerates. Causes an object to accelerate. So this is directly from A is equal to F over M, F net, over m. So you've got outside force that causes a net force that's not zero, gives that object some acceleration. If we have acceleration, well, here's the thing. Acceleration means that we have a change in velocity. And we all know that kinetic energy is related to velocity. So if you have a change in velocity, well, hot diggity, you also have a change in kinetic energy. So here's the game. In a closed system where you have no outside forces acting, then the energy is conserved. That means that the amount of energy in the system stays the same. If you have an open system where outside forces are allowed to act on an object or group of objects, then an object can accelerate, in which case you have a change in kinetic energy. We'll do some examples in a minute, but let me give you one more scenario as well. Scenario number 2 could be that a force causes an object's position to change. For example, to go from right at the surface of a table up half a meter. If you do that, we're changing the height of the object relative to some h equals 0. And as a result of doing that, well, that means that we're also changing the gravitational potential energy of the system. So kind of putting all of this together, and there are some other examples, but these are 2 really good ones to kind of start our conversation today and tomorrow. Kind of putting these 2 ideas together, here's the big deal, is that an outside force acting on a system I'm going to say over a distance. We'll talk about what that means in just a minute. Changes the system's energy. The moral of this story is that it's really important when you're taking a look at a situation to figure out if you have a closed system, again, one with no outside forces, or an open system, one with outside forces acting. Okay, so this idea of changing a system's energy by having a force that acts over a distance gives us a brand new word to talk about. You know, we've been trying hard in here, we've been doing a lot of things, but today is the first day that we genuinely and really are talking about work in the physics sense. I know you guys have been working hard all year, but right now, today is the time when we're really starting to talk about work. Okay, there are 2 definitions for work that I'm going to give you. The first one, work is marked with a capital W. Okay, one of the reasons that we don't ever use the word weight when we're talking about the force of gravity, because work stands for, or W stands for work. Well, we know that a force acting over a distance changes the energy of a system, so work is equal to delta E. Now, you guys, when I was in college, I had a professor that would go over and over this and would talk about how important it was, and I always rolled my eyes because it looks so simple. But it really is, it took me a while to figure it out, but it really is a pretty fundamental and important idea in physics, and honestly, in all of science, okay? So much so that it has a name, even though it's just 2 things being equal. The 2 things that are equal are work and energy, and this is called the WorkEnergy Theorem. It's called a theorem. It must be important, huh? Yeah. All right. So I want to take a look at a couple of examples to go with this, and then we will, I'll give you the other definition for work as well. So I've got a couple of examples. I posted a PDF of some example problems. If you saw that, awesome, and printed it out, go ahead and pull it out. If you didn't, you can pause, go to Canvas, print out the examples, or just look at them so you can kind of follow along with what we're doing. All right. So the first one that I want to look at is an example of a car. We've got before and after snapshots of the car's velocity. All the cars have the same mass, it says here, okay? And I would really encourage you, as you're working on this, to pause a little bit, work on it, and then check with me, as opposed to just listening to me talk about it, okay? Remind me tomorrow and I'll tell you about Bob Ross. Okay, so that'll make sense once I explain. Okay, so anyway, the situations below are before and after snapshots of a car's velocity. It says rank the work done on the cars to create the changes in velocity. So the things that can do work on a car would be the accelerator, right? That's applying a force to the car, an outside force, or the brake, right? That also is applying a force to cause a change in velocity, okay? So we want to know the work done on the cars to change their velocity during the same distance traveled. So we're just going to take a look here and remind ourselves that work is equal to change in energy. And in this case, the energy that we're talking about, it's not going up a hill or anything. So we're not talking about gravitational potential. The only other one we've really played with so far is kinetic. So we're going to say that work is equal to the change in kinetic energy. So that really just means that work is equal to kinetic final minus kinetic initial. Okay, and I, again, would encourage you to pause. Go ahead and try this out for a couple minutes, see how you do, and then come back and chat with me and see if you got the answer. So hopefully you've done that, and you're back now. Yay. All right, so work is, so that's 1/2 mv final squared minus 1/2 mv initial squared. Okay, there's a 1/2 m. The 1/2s and the m's are all the same for all the cars because it says they have the same mass. So really we can just square that velocity. The key here, friends, is squaring it before you subtract. I think we did a problem like this already this year, but we're just going to go through this real quick. So squaring that is going to be 400 minus 100 gives us some value of 300 that means something to us, just relative to the other things. After here is 0 minus 100. So this one's interesting because I get a negative answer. I am doing negative work because the force that's being applied is in the opposite direction to the distance that I'm traveling. So even though the car is moving this way, so that's the way that my change in velocity is going, the force is pushing back in this direction. The brake is on, right? We're going from 10 to 0. In option C, we have a kinetic energy at the end, well, a velocity of -10. When we square that, that gives us 100. And before, hey, it was 100 as well. So in this case, this seems a little bit funny because they've turned around, but the work done is 0 because the change in kinetic energy is 0. The speed is the same, which means the kinetic energy is the same. And oh my gosh, if you look at D, kind of the same situation here, right? So we've got 20. Oh wait, this one's going in the same direction, 20 and 20. Again, 0 because the speed has not changed. So we can rank these up real quick. Looks like A is going to be the biggest, and then C and D. And then finally, oops, is greater than B because again, B is negative. Okay. Ranking tasks are great. Energy bar charts are great as well. I think I've shown you things kind of like this before. Oops, we're going to start with A here. Okay. We did some energy bar charts with potential and kinetic a little while ago. We'd also done some with momentum. These are pretty straightforward, and I really like these because they're really nice to be able to see how things work. So work, get it? So work is equal to change in kinetic energy. We can also say, though, so that's kinetic final minus kinetic initial. We can rewrite this to say that the initial kinetic energy plus some work being done is going to give you the final kinetic energy. The way that these things are written, they use KE instead of K for kinetic energy. I just want to make sure that that makes sense to you. So the way these are set up, so you've got kinetic energy plus work is equal to final kinetic energy. So that's kind of the structure of those charts. It says the velocity of a tugboat increases from 2 meters per second to 4 meters per second in the same direction while a force is applied for 20 seconds. Complete the work kinetic energy bar chart for this process. The bar heights should be in the correct proportion to one another. So here's the game. The bar heights should be in correct proportion to one another. So the numbers really don't mean anything, but it's the proportions that matter. So if we take a look at the kinetic energy of the tugboat before, it's 1/2 mv initial squared, and we've got 1/2 m, and the velocity is 2. 2 squared is 4, but if you take 4 divided by 2, we get something like 2m is maybe how we would quantify the kinetic energy. And I think that that's what they did here because they have a bar that is too high. Okay. I know that work has been done because it went from 2 meters per second to 4 meters per second, but I don't know how much. The easiest way to find out, friends, this is why we do it this way, is that we can look at the final. So at the end, we've got 1/2 mv final squared, 1/2 m times, well, that's going to be 4 squared. So that's 16 divided by 2 is 8m. So there is my kinetic energy after. And it looks like we've got 2 bars here for that first one, which means we're going to have 8 bars. 1, 2, 3, 4, 5, 6, 7, 8, all the way up here. So this is the amount of energy that we have after. And then it's just a simple problem. So we've got 2 bars of energy, plus we need to have some work done to give us 8 bars of energy at the end. We can all figure that out, right? 2 plus what equals 8? I'm going with 6. 1, 2, 3, 4, 5, 6. Over and done. Okay? So there you go. That is how you set up a work or an energy bar chart or a work energy bar chart for just a kinetic energy system. There's a part B to this, and I want to take a look at this real quick. So in this case, it says we've got, it's the same tugboat. I think it's just a different part of the story. We've got 2 meters per second here, and we've got 4 meters per second here. It's the same speeds. Do you notice that? It's going in the other direction, but it's the same speed, which means that it has the same kinetic energy. So here is the funny thing. Even though it's turning around, because remember, it's just about the speed for the kinetic energy, the graph is going to be the same as above. And why is that? It's because energy is not a vector. Energy is not a vector. That's cool. In both cases, the speed doubles. And in both cases, the kinetic energy quadruples. That's kind of important to know, that the kinetic energy, the amount of energy that that system has, goes up by a factor of 4 when the speed just doubles. That's kind of a big deal. So I want to make sure that that kind of makes sense to you. Okay? So those are 2 good examples to take a look at with the work energy theorem. I did promise you, though, that there were 2 definitions for work, so I've only given you one. I need to give you another one here so that I'm not lying to you. So another way to quantify work, well, it's the way that we kind of set this up to begin, an outside force acting on a system over a distance. So the deal is that if I apply a force to something, like in these 2 cases, causing an object to accelerate, like, I don't know, maybe that car or the tugboat, I can change the energy. And in this case, I have a force that's like lifting something up, changing the position. Okay, again, I'm acting over a distance, and in each of those cases, I am changing the amount of energy, and thus I'm doing work. So work is equal to force times distance. Okay, so it's a force applied over a distance. Okay, I'm just going to write that down. So it's a force applied over a distance to change a system's energy. And I'm using object and system kind of interchangeably, mostly because we're talking about one thing that we're quantifying the energy for. Okay, so let me give you another quick example here to take a look at. So this is the bar chart on the back page of the examples, or the second page, I guess, that I posted for you. So in this case, I've got a block that's being pushed so that it moves up a smooth, frictionless ramp at a constant speed from A to B. It says complete the energy bar chart for the Earth block system. Earth block system means that we've got the gravitational force that's, changing that gravitational potential energy as part of the situation here, okay? And we're looking at it from A to B. It says put the 0 point for the gravitational potential energy at A. So we're calling H equals 0 here, just so that everybody's calling it the same thing. If you want to pick something different, you totally can, but it's going to change the situation. So go ahead and give that a shot yourself, and then when you're ready, then check back in. All right, so it says that the block is moving at a constant speed, which means that it definitely has kinetic energy. How much? I don't know. I'm just going to pick an amount. This looks like 1, 2, 3, 4, 5, 6 blocks of kinetic energy, and it has 6 blocks to start because it had some energy. No matter how much it starts with, it says it's moving at a constant speed, right? It said that somewhere. There it is, constant speed, which means that at the end, hot diggity, it's got to have the same amount of energy. There it is. Same. So those two have to be the same because the speed is constant. Speed or velocity is constant. But while that's happening, there is a force that's pushing this block up the hill. Okay, so there's a force that's being applied. There is work being done because when the block is at A, there is no gravitational potential energy. In this situation, they throw spring potential in there. We haven't talked about it yet. Give me a couple days and we totally will. But for right now, we're going to leave that out of the situation. So we've got gravitational potential energy is 0 at the beginning, and gravitational potential energy is something at the end. How much? I don't know. Let's just pretend it's 3. The 3 and 6 have nothing to do with one another. Those are arbitrary choices, but however much gravitational potential energy that has at the end, that's how much work we had to add. Because again, same kind of idea here. Work equals change in energy. So the total energy before, we'll say, I'll write it this way, energy total initial plus the work done has to equal the total energy at the end, okay? So now if we count up the boxes, so this is kinetic plus potential plus something we don't know plus work equals kinetic plus potential plus something we don't know at the end. So we've got 1, 2, 3, 4, 5, 6 blocks plus 1, 2, 3 blocks gives us 9, and that's the same amount that we have at the end. So these two have to be the same as well. Okay, so there you go. That's another little piece of the puzzle. Okay, we're going to keep on cruising here, my friends. So I said that it was a force applied over a distance, but there is one caveat with that. And generally when I do this in class, I've got this cute little cheeseburger demo, so I'm going to just kind of reenact it for you here on the computer. Can't wait, right? So I don't really have a real cheeseburger. It's actually a squeaky cheeseburger like you'd give to a dog, but it gets the point across. So let me just give you an example here. So if I take a cheeseburger, here it is. There's the bun and the meat, and it can be, veggie burger, whatever you want it to be. There it is. And it's sitting down on a plate. Okay. And I'm going to lift it up to a point up here that's closer to my mouth so that I can eat it. Okay. In doing that, I apply a force, Fa, over some distance. And do I do work? Indeed I do, because I changed the gravity of that cheeseburger. I applied a force over a distance, and I did change the gravitational potential energy of the cheeseburger. Therefore, I did work on the cheeseburger. Okay, so that's example number 1, lifting a cheeseburger. Let me give you another example, though. Example number 2. Let's say that you are at some sort of fancy cheeseburger restaurant where instead of ordering at the counter, they carry the cheeseburgers to you. So now you are imagining and let's make this an even more fancy place. Let's imagine that the waiters and waitresses are skating on roller skates as they bring your food to you. So here we go. So we've got this fancy waitstaff that has got your cheeseburger, and maybe it's on a plate. Let's imagine they're not just carrying it on their hands because that would be awkward and gross. Okay, and they're going to carry this cheeseburger from the kitchen to your table and hand it directly to you. So there it is, and let's put the cheeseburger back on there. So here it is. And there, oh, it kind of got smaller. I hope they didn't eat it on the way. There we go. So they are traveling a distance, right, to get the cheeseburger from the kitchen to your table. Are they applying a force? Well, sure, they're applying a force. The force that they're applying is this way, right, so that the cheeseburger doesn't fall because, the earth is also pulling on the cheeseburger. So they're applying a force, and they're doing that over a distance. But if they move at a constant speed, that's why I put them on roller skates, okay? That if they're moving at a constant speed, going from the kitchen to your table, are they changing the gravitational potential energy? No, because they haven't lifted it up or down. Are they changing the kinetic energy? No. So in fact, the fact that I've got my applied force perpendicular to my distance means that, dun, 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 no work is done. So this is a little funny. Look at what we have here. This said that it's a force applied over a distance, but it's not just that. It's to change a system's energy. That's the key, okay? So we've got a force applied over a distance here. Yep. A force applied over a distance here. Nope, because there's no change in energy, okay? Let me give you one more piece to this. Let's do example number 3, situation 3. Your little brother is a very picky eater, and there's the plate, and it's been set down now on the table. Okay, and here's the table, and there's the cheeseburger. The problem is that your little sibling, I can't remember if I said brother or sister just a second ago, doesn't like pickles. And oh my gosh, you guys, this burger has pickles on it. And so they say, no, thank you. And they push that burger away across the table. And it's got friction, so it's not going to go spill in anybody's lap, I hope. But anyway, so here's the cheeseburger now. And so they're applying a force in this direction, causing the cheeseburger to move a distance in the same direction. Friends, are they doing work? Indeed. I just said it was a friction-full table, but let's imagine it doesn't have friction just for a moment. That sounds like a dangerous plan. But let's imagine if they apply a force over a distance, that cheeseburger is going to start to move, and there it goes. So did we increase its gravitational potential energy? No. But did we change its kinetic energy? Yes, we did. So a force applied over a distance, again, does work. Here's the key. I don't know if you see this. I don't know if you've caught on yet. But in this case, the distance is this way, the force is this way. The distance is this way, the force is this way. In both of those cases, the force and the distance are parallel. I'm going to alter the definition of work that we wrote down here. I'm actually going to pull this over here and write down work is really equal to a force times a distance. I write when they are parallel. That's the thing that makes the most sense to me. In your book and a lot of other places, they will write force times distance times the cosine of the angle in between them, theta, okay? When theta is 90, as in example 2 right here, okay? If it's 90, then there is no work done because theta is equal to 0, or excuse me, cosine of theta is equal to 0. Okay, so that's just a kind of a way to look at that so that it makes a little bit more sense. To get your head kind of around that a little bit more, we're going to take a look at a ranking task. So this is the third one in your pile of things. So here we go. Let's take a look. It says, in the figures below, identical boxes of mass of 10 kilograms, okay, so they're all the same, are moving in the at the same initial velocity to the right on a flat surface. The same magnitude force F is applied to each box for the distance indicated in the figures. The task says to rank the work done on the box by F while it moves the indicated distance, okay? So I'm going to ask you to pause the video for a second, see if you can answer these questions, and then turn it back on. All right, so if we take a look here, we're going to remind ourselves of what we just said before, which was that work excuse me, is equal to force times distance, where the force and the distance are parallel. Or I guess I could say the force and the distance, the components that are parallel. So if we take a look at A, it's going to be the force of F times a distance of 5. So we'll call the work F times 5. In B, the work is F times 10. And in both of those, it's pretty straightforward, right? So in both of those cases, it's like your sibling is pushing the cheeseburger away across the table, okay? In C, now we've got a force that's acting at an angle. So not all of that force is doing work, right? Only the part that is parallel to the displacement matters. Now, I don't know what that force is or even what that angle is, but I can definitely say that the work is equal to, well, it's the force times the distance times, I'm going to go ahead and write this as the cosine of theta. That's definitely going to be less than A, where it was just F times 5, right? So we can kind of gather what's going on there. D and F look very similar. In both D and F, the work is equal to, so that's the force times the distance, but friends, the cosine of 90, we said is 0. So the work in this case is 0. So any motion that box has is not because of work done by that force. Same in F. You can talk about this one in the same way. You can say that work is equal to force times distance, but again, times the cosine of, you can call it 90, you could call it 270 if you want to be really clever. Either way, it's 0. So again, the work is 0. Okay, and then one more here for E. So E is You've got the force that's acting in the opposite direction. So this would be like a frictional force, right? That's what's kind of going on here. So you've got E is work is equal to force times distance times the cosine of 180 degrees, because that's the angle between them. So you've got F times 5 times -1. So it's going to be negative F times 5. So then if we figure out that work, well, we can do that pretty easily. That's just going to be negative F5. So we can rank these. Here we go. So we got B is greater than. Looks like A is going to be the next one, and then C, because those are all positive. D and F are both 0. And then finally, you've got E, and E is negative. So there's your last one. Friends, I want to say thank you very much for sticking through. My ask of you is that you send me an email once you get to this point in the video and tell me what your favorite holiday tradition is. Have a great night, and I'll see you tomorrow. Be well.